Dear students, hope the concept of number system and the basis of the number system are very clear to you. In today's session, we will learn about the number codes in binary number system. As it is clear to you, to represent decimal numbers from 0 to 3, we need 2-bit binary system, obviously having 0 and 1. 0, 0 is represented for 0. 0, 1 is represented for decimal number 1. For decimal number 2, we use 1, 0. For decimal number 3, it is 1, 1. In the same manner, we need 3-bit binary system to represent 0 to 7 decimal numbers. It means total 8 numbers. Further, if we use 4-bit binary system, we can represent 0 to 15. It means total 16 numbers. In other words, to represent 2 to the power of n numbers of decimal, we need n bit of binary system. Now from here onwards, in our general discussion, for all our examples, we will use decimal numbers 0 to 9. It means total 10 numbers. Hence 4 binary digits will be used. As we know, the number with base 10 are known as decimal numbers, and the numbers with base 2 are known as binary numbers. In decimal, 0 to 9 digits are used, whereas in binary, only 0 and 1 are used. While studying both numbers together and converting one system to other, it is important to take care when a number is a mix of more than one digit. For example, 0 to 9, all numbers are having only one digit, whereas 10 onwards, it is combination of two digits. Now we study a sample case of 13. To convert decimal number 13 to binary, we have a method like this. 13 is divided by 2 and remainder is noted. Now, quotient 6 is further divided by 2 and the remainder is noted. Repeat the process to end the dividend. Order the remainders according to MSB to LSB, starting from bottom to top. The obtained number 1101 is the binary equivalent of decimal number 13. But 13 is combination of two decimal digits. Now the concept of BCD comes in existence. BCD is binary coded decimal. It is not a number system like binary. It's a code. And by its common rule, only decimal digits can have this code, not the combinations. It means more than number 9 do not exist in this system, or we can say we don't care them when we are using 4 bits. Then to convert 13 BCD, we have to convert 1 and 3 separately to BCD. Like 1 is 001 and 3 is 0011. Then BCD of 13 is 001 0011. It is very clear we are using now 8-bit system. Here we have a table of decimal numbers to start. Now we will discuss the binary codes. The system having binary digits with a set pattern and its common rule is known as binary codes. For example, 8421 BCD 2421 5211 EX3 gray. These are some of the name of the coding systems which we will discuss in today's session. To study scientifically, we can classify the codes. First classification is according to weight of the code. It is known weighted code system. The value assigned to a consecutive places in the binary system is known as weighted code system. In binary system, the weight of the two depends upon the place it occurs. As counting from right, at first place the weight is 2 to the power of 0. Moving towards left, the weight is 2 to the power of 1, then 2 to the power of 2 and 2 to the power of 3 and so on. After simplifying these values, the weight comes to 1, 2, 4, 8 and so on. That's why it is named as 8421 system for 4 bits. And because the significance of the system is weight, so it is classified as weighted code system. We can take the reference of Hindi system इकाई, दहाई, सैकड़ा, हजार to understand this. For example, in decimal number 5489 means 5489, the weight of 9 is 9, whereas the weight of 8 is 80, weight of 4 is 400 and weight of 5 is 5000. In this way, we can find the binary code for any decimal number in 8421 system by putting 1 under the appropriate weight place. For example, to find out the coded value of decimal 0, we can say the weight of every place is 0. For decimal 1, we put 1 under the weight 1 and 0 to other places. For decimal 2, we put 1 under weight 2, making the code 0010. For decimal 3, we put 1 under 1 and 2 both to provide total weight to 3 and other places will be 0, making the code 0011. For decimal 6, we put 1 under 4 and 2 to get weight 6 and the code 0110. For decimal 7, we put 1 under 4, 2 and 1 to find the total weight 7 and the code 0111 and so on. There may be other coding system in weighted code category like 7421. Method to find the code are same as 8421. Another coding system is 5421. It is also weighted code system and find the numbers as previous. We can have negative weight system also, like 8, 4, minus 2, minus 1. The method of finding the code will be same, means the total sum of the weight of the code will be equal to decimal number. For example, for decimal 1, we don't have 1 as weight in this system, but the sum of 4, minus 2 and minus 1 comes to 1. Then we put 1 under 4, minus 2 and minus 1, getting the weight 1, and the code will be 0, 1, 1 and 1. Another weighted code with negative weights are 7, 4, minus 2, minus 1. Finding the values are the same. Now we learn about non-weighted codes. Some of the codes do not follow the weights of sequence of binary number, such as codes are categorized as non-weighted code like ASCII, Gray are some example. These codes are very useful because of their other unique properties. We will discuss it further. In non-weighted category, we will discuss XS3 code, sometimes abbreviated as EX3 codes. Such codes are found by adding 3 to each digit of decimal number. In our first example, 0 of decimal first converted to binary, then BCD 8421 coding system. After that, by adding 3 to 0 or 0011 to BCD, we can convert it into EX3, which is 0011. In our second example, decimal number 6 is converted to EX3 by adding 3 to the decimal. In third example, decimal number 15 taken. In this example, we will add 3 to 1 and 5 separately. By doing this, we will get 4 in place of 1 and 8 place of 5. Now, 4 is converted in binary and 8 is also converted into binary separately. By putting both the values together, we will get XS3 code of 15. Now we will learn the reverse action of XS3, means the example given is an XS3 number and we have to convert it into binary or decimal. Remember, binary equivalent of 3 is 0011. In the given number, there are total 5 groups with decimal. We will subtract 0011 from each group. We will get 1001, 0111, 0000, 0100 and 0010, another set of 5. Further, converting each group into decimal, we will get 9, 7, 0, 4 and 2, which indicates the number 970.42. Now we'll define another property of binary codes. Reflective codes gives us a reflection of its own. A code is said reflective when it is self-complementing. We have to understand complement number here. If we start from decimal number system, the sum of 0 and 9 is 9, which is the biggest number of the system. The sum of 1 and 8 is also 9, and in the same manner, sum of 2 and 7 is again 9. Such numbers are called the complement of each other. 3 is complement of 6, 1 is complement of 8, 4 is complement of 5. The system having this property is known as a reflective system. According to this, if a binary code 0 is complemented by its own 9, 1 is complemented by its own 8, and so on, then the code is called self-reflective. EX3 is example of it. While studying a binary number, we have to remember there are only two digits 0 and 1. So 0 is complement of 1 and 1 is complement of 0. With the help of this chart, we can get more clear picture on it. See the EX3 codes for 0 and 9. These are 00, 11 and 1100, means zeros and ones are complementing each other. Now see the light orange bands 0100 and 1011. So 1 and 8 are complementing each other. In green band 0101 and 1010, so 2 and 7 are complementing each other. It is easy to understand how blue band and pink bands are complementing each other. So we can call EX3 is a self-reflexive codes. This makes it unique. EX3 is non-weighted self-reflexive binary code. We can have self-reflexive codes in weighted code system also. Take the example of 2421 codes. These codes have their own unique property. As it is clear, the weight of second and fourth bit is 2. We'll give priority to the lower weight and then the property of self-reflection. Check decimal number 2. We can write 1 at second and fourth place 2. But the lower weight will be the right place. Up to 4 you can go at your own. Now see number 5. Here you may opt first and third place to get weight 5. And second option available is first, second and fourth place to get 1, 2 and 2. Total weight of 5. Now apply the property of complements. 5 is complement of 4 and the code is of 4 is 0100. Simply complement it. You will get 1011. This fulfill your both the conditions, same as 6, 7, 8, 9 are complementing 3, 2, 1 and 0, and also the weight according 2, 4, 2, 1. So this code is weighted self-reflexive codes. We can have another example of 3321 codes. These codes also having both the property of self-reflection and weighted code according to the system 3321. Now it's turn to discuss gray codes, which has another property which help us to reduce the switching operations. Gray code differs by only one bit in two successive values. You can see this table while moving 0 to 1 of gray code, only one bit has to change. Same as from moving 1 to 2, again only one bit has to change. You may understand it by watching further numbers. Take any example from 7 to 8 or 13 to 14 or 14 to 15. Now we can check how this is helpful to us in reducing the switching operations. See the binary code in 8421 system and take the example of moving from 7 to 8. And then take the same condition in gray. In 8421 system, you have to change 3 digits, whereas in gray it is only 1. This reduces the operation numbers at time as well and boosts the speed of the mathematical operations. Here we will discuss about getting gray codes from binary. It is done by following 3 steps. Take an example of the given binary number 1011. To convert it into gray code, follow the first step, that is record most significant bit as it is. Second step is add MSB of gray code, mind it, MSB of gray code to next lower bit. In this example, MSB is put under 0 and added. Be simple, ignore the carry. We will repeat the process again and put 0 under the next lower bit and add. Further, 1 is put under the LSB1 and added. Ignoring the carry, we will get 1110. So 1011 of binary is converted to 1110 of the gray. You can practice it at your own by taking different examples. Here are some facts. If we learn, will make the conversion easier. First fact is value of most significant bit never changes. And second fact is because we add 2 bits value without carrying the carry, so the function of XOR can be used without much pressure. We can understand the XOR function is detector of odd numbers of ones in the operation. It means the 1 is in odd number in the bits to be added, the answer will always be 1. So we can represent the conversion function as shown on your screen. By using these technique, you can better understand this table now. we have to learn how to get binary codes from gray codes. Take the previous example to get better concept. Give gray code number is 1110. The first step to record MSB as it is. Remember, while converting from binary code to gray, we have not changed the MSB. In second step, add MSB of binary. This is the main point. MSB of binary. This is the only point to be remembered. MSB of binary is to be added to the next lower bit of gray. Again, be simple, ignore the carry. We will get our answer 1011 of binary after conversion from gray. We can get a general function to convert gray codes to binary codes. Your screen is self-explanatory. In this screen, you can check all the codes discussed till this time in one place for your references. In today's session, we have discussed some of the binary codes which are mostly used, and it is in the scope of our syllabus. It is also to be in your knowledge that there are more binary codes are available and also can be generated as need arises. Here a tree is discussed for your future references. Also, it is to be understood that a code with more than one utility can classify under more than one category, as the case of XS3 codes. We leave you with a self-explanatory animated classification tree.